Right, is on. Well, thank you for having me here in Cambridge. This is going to be a tools talk. So I'm coming directly from the engine room, and I want to report that the engines are running smoothly. And so perhaps what you can take home from this is there are some tools that actually are quite nice, that fits exactly to some of the questions that many of us have been studying. My motivation for studying these problems at all, I guess, stems from that is, as we now know, in the way Hasselhoff and Lassen said it, it's a cyclotomic spectrum, or as Nikolaus and Scholz would say, a genuine cyclotomic spectrum. And I wanted to understand what is it about the category of spectra that makes this possible, and I know several of you have studied that question also. So I'm going to push, so this is harnessing homotopies. So I'm going to push as much category theory into the box so that we can harness the homotopies at the pairing point. And it turns out that category theory takes care of a lot. Also, I want to extend from HHH to, well, that's over the circle, and I want to extend to other groups, Lie groups, compact Lie groups. Okay, so what I'm going to say is actually just enriched category theory. So there are very few homotopies that are going to be seen here. So let's start at the beginning with an example I know you know. So everything comes from diagonals in the underlying category, say, of spaces. And that is, so if X is a space, then I can take the suspension spectrum of it. And let's see, S is a finite G set. And let N be a normal subgroup of G. I'm just introducing some metrics that I'm going to use all the time. Then I can consider the S-fold smash of this S module, which is the same as the suspension spectrum of the product. Some people have told us a lot about the geometric fixed points. And one of the things they always tell us is that they commute with suspension, so that this is actually the suspension spectrum of the fixed points, which we actually do know how to handle. Well, that's just, well, now it's a product over the orbits, which then becomes just the smash over the orbits of the original spectrum. So that is wonderful. And the geometric diagonal is a wee generalization of this, where we don't have exactly spectra like that, and well, and we worry a wee bit about how the S changes. So in the end, I'm going to want to have a correspondence between the geometric fixed points of the smash powers and the smash powers over the orbits. And of course, there are going to be some conditions that has to be satisfied. And why am I worrying about changing the S? So here's an example that tells us that we should be interested in changing our set. So if S is S1, and I guess I have to admit that that is a simplicial set, or even worse, the singular complex conjugalization of the simplicial circle. Those are simplicial sets. And if A is an S-algebra, then smashing over S1 is exactly a model, at least if it's cofibrant, a model for HHH of A. But of course there are lots of structure maps connecting all the sets that constitute the simplicial circle. So I'm very interested in what happens when I change the underlying set. So, a challenge, and I guess many people have done parts of this. I should say, of course, that this came out of thinking about Martin Stoll's thesis, where he does this, and I wanted to isolate. So some of the proofs are kind of hard to follow because they're just done. They have no structure. So I'm trying to put some structure to the game. That I didn't mean to speak badly about that. Thesis.
Luckily it's not recorded. Luckily it's not recorded.
And of course, everything is building on stuff that people in the audience know very well. So you will recognize your favorite models quite a lot. So construct a geometric diagonal it should be an isomorphism in certain situation, and it should be functorial in S. Okay, so there are maps that go directly from here to there, but I don't know any maps that go directly from...
On the left it's smash over X.
Oh, sorry?
On the left.
X. I don't know of any maps, direct maps, that are natural, but there are maps. So I'm satisfied with a span like this that is natural in S and isomorphism if A is cofibrant in some sense and S is free over N. Okay, so just so that nobody says that this is trivial, this is impossible. So I sent you there. Let's do an example.
Why can't you put a tree?
I'm sorry?
Why can't you put a point or something?
It should be an iso when A is cofibrant.
Ah, an iso.
Yeah, and luckily our theory does not factor over the trivial theory. We are very grateful for that. Okay, so let M be a symmetric monad. And for those, we know what the diagonal is.
What does symmetric mean?
Symmetric, okay, so symmetric, a commutative monad in sets. It's a abelian monad. Let it be in sets. It can be in any Cartesian closed category. Let's see. What does the diagonal do? Well, it takes a blue element. Here it is. it is indexed by the orbits. And it sends it to, well, what should I do? I can't do very much, but just smear that element over the orbit. So if this is S, and here we have all the n orbits, which of course map down to S modulo n, and here we have S, and we have X, S sitting there. So if I have any S in that orbit, I just put an X, S there. Now assume that I have a function S to t. So here I'm going to use that n was symmetric, because this then is functorial just as it was for, well, if A was commutative, then I could have done something more dramatic than taking, okay, so since I was that evil, I probably should say commutative. Then this is sent to the product in the t slot. It is sent to the product over all the x's that land in the orbit of t. And I have my diagonal. And that then is sent to, well, it's the same formula. I take the element I do have, and I smear it over the orbit. What happens if I go this way around? Well, let's see, I have that thingy over there, and that is then sent to the product over the preimage of t of the thing I've got there. I'm sorry. Okay, these two things are not usually the same. As you see, the indexing is different. However, there is some repetition here. I can write this in a way that is more similar to what's over there. I index it in the same way, but I need to repeat this. How many times do I need to repeat it? I need to repeat it, the isotropy group of Fs divided by the isotropy group of S. Okay, so are these equal? No, normally they're not equal. So there is no chance that the diagonal is natural. However, in some cases it is. So let's see, what is it? Of course, if the monoid is trivial, that's one example. Okay, when this is for you. And it's trivial. But it's a very good example because it actually is the heart of the reason why S modules have a superatomic behavior. It is true if N is a P group, where P is a prime, and we have that x to the P is equal to x all the time. This is actually an important and interesting example. I don't know for a fact, but I'm going to investigate, and anybody who wants to come along is welcome. I think this is actually the reason why topological cyclic homology of FP algebras behave totally algebraically. There's a third one, and that is, well, come on, if these numbers are equal all the time, then it's okay. And that is what's called in my tech notes a something, but which Sarah Niegel explained to us on the conference is called isovariant. It just goes to show that you can be confused if you're isolated in Western Norway. Don't know the name of things. Actually, isovariant, so there are various ways of saying this. I could say that, well, of course, this is always an inclusion, so if it's a bijection, then I'm okay. Or I could say that, okay, so here goes. F bar, if F inverse of T that always surjects to F bar inverse of the orbit, if that is a bijection. Or alternatively, if this thing here is Cartesian. And to tell you the truth, I didn't, as you can see, I didn't know about this notion. And I discovered it deep down in an argument where all of a sudden needed two things to be equal, and they only were equal if this were true. Yeah. So, examples of isovariant maps. Well, yeah, of course, the trivial map is. But apart from that, all inclusions. And so also all bijections. All maps of free instance. So that is partly underlying the reason why in some of the papers that people, including myself, have written before, have focused very much on the free case. That's partially because these maps are isovariant. And trivial sets. It actually is trivial. So there are lots of examples, and what is true is that, for instance, in a Cartesian closed category, the commutative or symmetric monoids have a functorial diagonal, as we just saw. And this is a special situation of something that I'm going to present to you today. So I'm interested in diagram spectra. So I should look at enriched functors. So, the theorem. So we're going to develop the thing that's in here, and then it's going to be a theorem at the end of the talk, hopefully. So, the category of S functors, and what is S? That is some closed symmetric monoidal category. It ought to have diagonals. It ought to have diagonals, but not so strong so it actually is Cartesian closed. So I don't expect there to be co-units. So for instance, pointed spaces would be a wonderful example. Perhaps a wee bit more, but not much more. From the category I to the base category. So this is then actually an S category. Has a geometric diagonal. And it's going to be a span. Here, in the Cartesian closed case, it didn't need to be a span, but here I don't know to avoid that, which is functorial. With respect to G, okay, so let's set the stage here. I've mentioned G here, but I can allow that to vary. N was a normal subgroup of G, and let's have a name for the quotient just to conform with some people's notation. And the functoriality here is with respect to changes like that, and that's going to be very similar to change of universe or whatever. I'm not going to talk about that, I'm going to talk about the other direction, which is more fun. And fixed G. So these can move simultaneously, but it's convenient to do it one at a time. Can I call this N isovariant? Because it doesn't really depend on G, it only depends on N. And it should be an isomorphism. So I can't really, at this level here, I haven't developed any model structure or whatnot. So I can't say with respect to the cofibrant, but at least I can say that it's an isomorphism with respect to the building blocks. And the semi-free, very similar to some semi-frees that we've seen before in spectra. On these, they are. The geometric diagonal is an isomorphism. And in the case where we have free action, then we can extend that.
So what was supposed to be semi-free?
On okay, so semi-free functors. So on objects here.
I'm confused. What is I and what is?
So I is, so since this is an S functor, this has got to be an S category enriched in S. And yeah, I appreciate your question. Perhaps I want some more on I. I want it to be symmetric monoidal. And for convenience, just now I want it to have diagonals. I don't really need all of that. But let's just assume it. So if you think of orthogonal spectra, this will then be the category of orthogonal representations. And that's, I'm sorry? Yes, it will be the top category.
And where does G come from?
Okay, so G, from now on, I will operate with a fixed group G that acts on everything.
Which acts on
Okay, so the point is that we're going. Okay, so actually, let me write it out. So we're going to have. So if x is one of these functors, I can smash it over S mod n. I will have a operation that is very similar to the geometric diagonal, or there will be a geometric diagonal. I can attack the S-fold smash of x, the geometric diagonal of that, and I will have that. And the point is that G acts on this.
Is semi-free something you're going to define later?
It's exactly what, okay, so think of a representable object. They're a wee bit more complicated than that. So there, you also must have a slot for adding cells and equivariant cells and whatnot. But apart from that, it's just, Brooke, are you the first to call it semi-free?
I have co-authors, I'm sure, but I don't even know if that is the first.
Okay, so.
No, I'm thinking of semi-stable.
Mhm.
Do we have semi-free?
I seem to remember that might have come from Quillen.
That become?
Might have come from Quillen, one of Quillen's papers.
No, he has quasi-free. That essentially means smooth in a non-commutative setting. Okay, so what is this good for? Well, one of the things that is good for is that, well, it could have been a setup for, okay, so such a theorem is good because it leads to the following theorem. For an S covariant orthogonal ring spectrum A and G compactly and there are some conditions on the compact Lie group that I don't know whether are true in general, but they're true for tori.
The conditions on a compact Lie group that you only know are true for tor.
Well, I know it is, and for finite, I know it, of course.
So you don't know them for SU2. I mean, okay.
Well, if you give me a particular group, I can worry about that, but I don't know it in general. I can give you the conditions afterwards, please.
And your co-authors too?
Yeah.
I'm sorry?
You'll give us the name of your co-authors afterwards.
BNS?
Yeah, so that is Brun and Stolz. And let's see, we should have, I hate this word, naively cofibrant G space X, then there is a natural isomorphism between smash over X of a geometric fixed points. Okay, so I should have a normal subgroup N, and that probably should be finite in order not to have too much extra noise. Like that, just so that you see that it's good for something. It's not complete abstract nonsense. Questions so far? Yeah.
So what do you mean by smashing A along X?
Okay, so if it's a finite set, okay, yeah, probably everybody will be more happy if I write it as a tensor. It's a tensor in the category of commutative algebras.
Oh, A is community.
Yeah. Yeah, so you can do parts of this associative for the circle, but of course if you want more general, you need commutative. So it was important that the X space was, the G space was cofibrant, because otherwise this will be very, very false. As a matter of fact, if it is true for X at point, then A is actually a good setup for then A modules, or A algebras is a good model for again setting up a cyclotomic theory. And I think some of you have explored that as well. That occurs in Schultz's thesis also. Okay.
What does naively cofibrant mean?
It means Borel. You call it Borel all the time, so it all consists of free cells.
So you could say free, couldn't you? Oh,
Yeah.
That would be too,
Too clear, yeah.
No, I see. Okay, so I was not the one who chose this. Okay, so the point I want to make is that there is a very natural choice for what's supposed to be there. And let's see. So if G acts on S, and here is S, and I have an X sitting here, perhaps it's slot S, what does acting by G do? Well, it sends XS, this tuple, it sends it to X G inverse S, that tuple there. That's how G acts if G is discrete. So it jumps. So it goes, it shifts via G, and let's see, we're interested in n orbits here, probably. So if these are n orbits, of course, it can skip from one orbit to another, and if I multiply by n, I just shift along.
So you don't act on the little x.
I don't act on, no, why don't I act on little x?
Yeah.
Why don't I? Let's act on little x. Very good question. So let's act on the next. And as an example of people who want to act on small x's, Ilhaken and Ravenel want to act on small x's. And they consider a situation where you have, well, here G is C mod 8, and S is 0, 1, 2, 3. So I have A smash A smash A smash A, 0, 1, 2, 3, and they want to act by the generator in C8. And of course, the thing to do is to send this over here, this over there, that over there, and that over there. Except, in their situation, A is a C2 spectrum. So, C2 acts on A. So I use the identity here, the identity here, the identity here, and twist here. Yeah, why don't we act on the small x's? So let's act on the small x's. And what is the proper setup for acting? I would say. Okay, so then actually I don't need to repeat the same A all the time, do I? I only need to repeat the same A in the same orbit. So what I'm interested in is things that, well, it's indexed on S, but the group G acts. So this is what the infinity people would call the homotopy G orbits of S, but we concrete people, we say that the objects, this is a category whose objects are S, and where the morphisms is G times S, thought of as a function like that. So it's a translation category if you want. Okay. Well, okay, it could be here, it could be anywhere. We're interested in situations like this, and we're going to smash them together. Yay. Do I need to do anything more before I set the scene? 2 pages to go, but there are 2 tough pages. Okay, there's going to be a huge diagram on the blackboard that is going to construct for you the geometric diagonal. And as I said, I hope what you can take home from this are a few truths. And so this is technical, I admit it, but it contains some small tweaks of old ideas. Okay, so I have such a device. Yeah. Okay, so I should remind myself how I construct this smash. In diagram spectra, I construct this smash as follows. I take the indexing category I and smash it with itself S times. I apply my X if I'm going to smash X with itself S times to I, and then I get to the spaces, and then I just smash them together. Or, and let me call the symmetric monoid operation in I to distinguish it, let me call it plus. I do plus in that direction, and I take the left function. That is the definition of the smash. So here on the right-hand side of the board is going to be something like that. Okay, the thing that people noticed very early on is that this thing here will actually, if I actually, let me do it S over N, because I'm going to do that in the end. So, okay, so let me do that. Okay, and remember that I had and G was acting on S. And this short exact sequence, the people who write papers call E. Okay, what they noticed is that inside I, if you consider the objects that come with a J action, but so the objects here are J objects in I, but I keep the morphism space that I had here, so this is fully faithful. But these are J objects in I, those are the objects, but otherwise it's fully faithful. I can do the same here. Well, I should take the left con extension of this thing here, but if I follow through with this, I actually land there. Okie dokie. So, here is the small tweak. You do the same with S mod N. And what is this category? I probably should explain all of these things. So, objects are just functors indexed on S mod N, but with this G action to I, let's call it B, and I, S, N, J, B, W is simply the smash of all the morphism spaces. So I have a map here, I call it IS mod N, and I have a similar map here, called IS mod N as well. So that just, what does that map do? Well, it forgets the J action, it just remembers what it does in objects. And let's see. I have my B, I put it there. So what does that B do? Well, originally B was here, but I can think of that just as well. As a functor here.
That's what the original B was?
That was what the original B was.
Still don't know.
No, this was what the original B was.
Still don't know what it is.
Okay, so what is that? That is a collection of functors indexed over S mod N, connected by action by J. So think of
So B was an object that we were studying, not a canonical thing.
No, B is the object we study. For instance, B could be the constant x over time. That is a possibility. And that is the application in the end, but the bookkeeping becomes horrible if I do that. So what does it do? Well, an element here is such a functor, and that is sent to, well, what can I do? can take B evaluated on S, and then I can evaluate that. It's the obvious thing to do. And I can do that here as well. Total honesty would require me to put an IS mod N. So smash here would send me to the J objects, and plus here would send me to the J objects down there. Okay, now we have enough functoriality to go all the way. I really want to write just S and a S up there, but perhaps I should modify that a wee bit using the Bell and May ideas again. I put a little E there. So ISE. The objects are these indexed families, indexed by S families in I, but the morphisms are simply well, but there is an N action on that, and I take N fixed points of that. So this is ripping off from Mendel and May, and we have, well, we have the projection. So the projection from S mod G to Sn mod J. So I get, just by applying that functor, I get functors like that, I get functors like that. I land here in IE, and I land here in SE. I could put a point here if you want to, that's the same thing, it doesn't change anything. So that is when S is the point, and if I don't write a point, I have exactly my Bell-May notation. Okay, of course there's a map going there so that this diagram commutes, but that's not what we're after. We're after the right adjoint. And Mendel may call that fix N. So that is the adjoint of right adjoint of the map that naturally goes in that direction. And okay, so it was not one of the things I declared, but I should assume that I also has the right adjoint down here. And now comes the icky part. Well, part of the structure is that there is a natural transformation in that direction. I should assume that there is a natural transformation in that direction. And why don't I just assume that both of these are isomorphisms? They are isomorphisms for all examples of interest. So that makes the final statement, and I have the time left, easier to state. I really don't need that there are isos yet. And by the way, now I can compare this. This is a span I can take a left con extension of. And notice that this is also a span I can take left con extension of, and they compare. Because, and the categorical people among you know this, but there are stuff that I don't know about left con extensions that I still discover. Okay, so what is true is that left con extensions are quite straightforward. So I make a category whose objects are spans like this of S categories. So those are the objects in my category, and the morphisms between two such fellows is a map in between here, an actual transformation here, and an actual transformation here. That is a morphism. That gives you a category. Okay, so that means that, what does that mean? That means that I get a map to this weird span. Let me call that. It's smart to adjoin it with a joined J there, just to remind yourself that this is the span of this thing here. And I have then a map to, what do I have? Fix and star plus star. Okay, so this thing here is then sent to B naught star A naught. So this is just notation for that span. Very good. Okay, so then going home is easy, but there is still one word. So that will give me the final span will then be, okay, so there is a colon limited stage there as well that I try to keep quiet about. That will take me all the way to the geometric fixed points of smash S, E, P. And this thing here is by definition what you get when you take the span with respect to fixed points in S and the fixed points in I. Okay, very, very good. So, why does that help us at all? That helps us at all because from S to T. So then I have one diagram like that for S, and I have one diagram like that for T, and here I have natural transformations. And yay. So what I must worry about is whether going from this span to that span and with that map is the same as going from this span to that span to that span. And then it turns out that the following fact is very, very useful. And I don't know why nobody told me about it and why I had to discover it myself. So can I call this L B naught X naught A naught, and this map L beta F alpha? Fact, if I'm in the following situation, you all probably Somebody has to say it. If I have two maps here, and I have a natural transformation between them, I have a beta prime here and an alpha. Then what is true? So the left conic extension is symmetric in the middle. You can change scalars back and forth. So I can use alpha and epsilon. Or I can use beta composed with u1 epsilon, f, and alpha. These two things are equal. So if you have something that looks like a dollar bill or something like that, you can switch one side to the other. Okay, and that's exactly what you need here. It's going to work splendid if it's not going to work in general. Remember, it doesn't work in general. It works if you are in a diagonalizable situation. And what is the diagonalizable situation? Okay, so I have to transcribe what I have here into what I actually have had time to say, so I have to translate. So let's see, so A is a symmetric monoid or ring spectrum in IV, and what do I need? I need that the following diagram commutes, and it's a sort of a weird diagram. Okay, so let me actually start down here. So this is exactly the same sort of problem you had for the monoid. I can multiply all these together. Where do I get? I get here, because that's how multiplication works. And I can go by the diagonal in spaces, or in S, to and I can multiply. Okay, so I have a diagonal on I, so I can take A and use the diagonal there. The commutativity of that diagram is exactly what is pushed into here to show